Welcome to the 17th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about Chapter 12, Particles in Boxes and Their Applications. This is the last chapter in the second part of the book, which was the fundamentals of quantum mechanics. After that, we're going to go into the third part of the book, which is advanced methods. The two images I have for you are the wave functions of a particle in a finite square well. You can see that the wave function extends out into that forbidden region, which is shown in gray. And then the image in the center is an image of how we do a proof that all boxes in one dimension and in two dimensions, no matter how deep they are or how shallow they are, they always contain at least one bound state. So Chapter 12, Particles in Boxes and Their Applications. Now, I note that when we solve particle in a box using operator methods, as opposed to being the simplest problem in quantum mechanics, which it is for differential equations, however, I do caution you that there are lots of subtleties with the proper way of understanding the solutions of the differential equations that often aren't talked about in other quantum mechanics books. For operator methods, this is actually one of the harder problems to solve. Schrödinger called it shooting sparrows with artillery. All right, so it's really not that bad, but you have to have the right idea to be able to figure out how to do it. That was highly non-trivial for Schrödinger to figure out. So we look at the particle in a finite square well as well. Schrödinger did not do this. This was something that we worked out. There's some others who also had ideas related to it, but they didn't quite get all of the details fully explained. So we did this. This is one of the first problems I worked on to solve when I knew that, yeah, I think I can actually do this book project. We look at it in higher dimensions, not just one dimension, two dimensions, and three dimensions. We look at the interesting question of what does it take? How deep does a potential have to be in order for there to be at least one bound state? We talk about uncertainty and other subtleties related to these different solutions that we're finding, not just for particle in a box, really in general. And then we answer the following question, which is why are eigenvalues sometimes discrete and sometimes continuous? And I think most quantum mechanics books do a poor job at explaining this. They often use some image of a wave function somehow fitting into the potential well in order to describe why you get discrete energy eigenvalues, but then they don't really explain why other times they're continuous, like in the Coulomb problem, where you have an infinite number of bound states, but you also have a continuum of states as well that lie at higher energies. So that's one of the topics that we talk about in this chapter. All right, guys, let's go browse through the chapter. Our quote for this chapter is from Sonia Sotomayor, United States Supreme Court Justice. "You can't dream unless you know what the possibilities are." So we start with a particle in a one-dimensional box. This is what the box looks like. That's what the wave functions look like. The way that we have to solve this is a little bit complicated because we have to use a trigonometric function and some important trigonometric identities in order to make it work. Our ladder operator takes this form with a superpotential that is a tangent. There's also a form that has a superpotential that's a cotangent that can be used. This is not something you would just think of off the top of your head. But what's interesting is, in addition to solving the particle in a box, we also solve all of the problems that involve what are called Paschal-Teller potentials, which are secant squared potentials. Those are the auxiliary Hamiltonians that we solve in addition to solving particle in a box. I had mentioned before that when you solve problems with a factorization method, you solve a whole family of problems. And this is actually a very interesting thing. You never would know that structure is present with the particle in a box unless you solve it with the factorization method. So this is one of the real benefits of working with the factorization method. Okay, after solving for particle in a box, we look at the particle in a finite square well. This cannot be solved by the factorization method in all space because the potential has a discontinuity in it. So we have to use a method called single-shot factorization that allows us to solve it. And we, in essence, solve the problem all at once for all of the energy eigenvalues and energy eigenfunctions. This is a different way of doing factorization than the way Schrödinger did it. We have to solve a famous transcendental equation that looks like this, and the place where the lines cross, that is the place where we have solutions to the problem. That's where the energy eigenvalues come about. So this is an interesting new twist on how factorization works, and it's required for the particle in a box. This is a way of looking at the bound state energies for the one-dimensional case. And then after we've gone through this, we then go ahead and repeat this in 2 dimensions, looking at circular and spherical boxes in 3 dimensions as well. So we look at the particle in a 2-dimensional box. This requires us to work with Bessel functions. There's no escaping it. I do carefully get you through what the Bessel functions are. They essentially look like sines and cosines, but they decay rather than having a constant amplitude as the argument gets larger. They're not something to be afraid of, but you do need to work with them in order to do these 2-dimensional problems. Then we do the 2-dimensional problem in a finite square well. This again is going to be done using our single-shot factorization method. We get a similar kind of transcendental equation that we have to solve. It always has at least one solution, so there's always at least one bound state. But that bound state energy can be exceedingly small if the potential well is not very large. We then go ahead and look at the particle in a 3-dimensional well, both in a box, which was 12.5. I blew past that, and in the finite square well, which is 12.6. In this case, the potential well has to be deep enough, otherwise there is no solution. And so we have this interesting conundrum where in some cases there are solutions, in other cases there are not. And then we look at this question of the existence of bound states. When can we find at least one bound state? To solve this problem, we have to use the variational principle. So we first talk about what the variational principle is. It's often used for approximations. When it's used for approximations, you almost always have to use calculus. We do have a couple of examples that we can do without calculus, but in general, you have to use calculus, so it's something that we're not going to talk about here. But when you want to ask, does this dash potential have a bound state? Because the dash potential is lower everywhere than that finite square well, and the finite square well does have a bound state, we can use that to prove that that dash potential has at least one bound state. And that's a really cool argument. We go through the mathematics of that argument very carefully. And then we get into talking about uncertainty. There's a lot of interesting questions related to uncertainty. In addition, we get into having to do a little bit of math that is related to integral calculus, but it really just involves looking at sums of powers, so we can do that using techniques that are similar to our geometric series in order to evaluate it. These ideas are also going to be important when we look at time-dependent problems. We're going to have to do some summations of exponentials and of cosines and sines, and we show how to do that. Then we get into a little bit of the philosophy. Why are some eigenvalues quantized while some are not? I really like this chapter and this discussion. I hope you will as well. There's a little bit of philosophy to it. There's also a little bit of math that helps support the arguments that we give as to why you sometimes have bound states and you sometimes have continuum states. And that's the end of the chapter, and that's the end of part 2, our fundamentals of quantum operator mechanics. We then will move into part 3, which is advanced techniques in quantum mechanics, and we get pretty advanced. Some of the material that we cover you won't find even in graduate level quantum mechanics classes, but because the techniques that I've given you are so powerful, they will allow you to work on these problems. And we'll be talking about those in subsequent videos. Hey guys, let's do quantum right.